different things happen if you look at a rapidly rotating star versus a binary interacting star. So we'll have a direct comparison of what that looks like to the populations as a whole. Yep.
Even leaving aside completeness, how large does a population have to be so that you're not Poisson-dominated? These stars are all pretty rare.
So I would check out Trevor's paper because he actually does, especially in this new one, look at Poisson statistics and how that's affecting what you're doing. For example, not finding any Wolf-Rayet stars could mean that there are literally no Wolf-Rayet stars. It could mean that you are missing a few just based on sampling errors. So that's actually considered when we look at this. You could do it for something with the population size of Westerland 1. A very tiny OB association is not going to be enough. Ideally, what you'd want is large populations where you have some understanding of the star formation history. But it's enough to, at the very least, constrain scenarios that aren't reasonable in terms of explaining the populations. Like, for example, if you had a all-binary population where all the binaries are interacting and you predict huge numbers of yellow supergiants, which is one of our results. We know that's not true because we see so few yellow supergiants. So it's somewhere between constraining the binary fraction and nailing down the binary fraction depending on how good the observations are. Yeah?
I love this. So you have 4 observables, or potentially observables, O stars, blue supergiants, red supergiants, Wolf-Rayet stars.
We have many more. This is just the prettiest one.
But of these 4, I think stellar models have some predictive power for 3 of them, and the blue supergiants, it's actually this quote from Kippenheimer that you started with, it's magnifying glass, it's mostly, this relates to this blue supergiant, so it completely blows up, even if you take extra mesh points in our models, we already get different answers, right?
Yeah.
So I'm wondering how much you can do. Do you discuss this with, I know this is JJ's models, which of these are the ones we are so confident that you can actually use them to test, and which ones maybe the theories should interact together first before you start comparing with the data?
Yes, so we do talk about, and like JJ's models talk about this, and then we reiterate it in the papers, and like the Geneva models have issues with the blue stars too. Which populations we would be more or less confident in terms of, for one, observations, and then 2, what the models are predicting. I'd also check out how we define blue supergiant, because there are B stars, there are all supergiants that are blue, there are bright blue stars, for anybody that's been following LBV arguments recently, which are a new version of blue supergiants. So Trevor's very particular in his definition of just a temperature range, and they're not the blue loop stars, which makes life easier. They're basically the lower mass main sequence stars. But yeah, I think part of that is being able to define what we call a blue supergiant versus what we observationally identify as a blue supergiant. Here they should be mainly main sequence, but the evolved blue population gets messy quickly. So another question about binaries, bringing this back to red supergiants, is that we know red supergiants should be strongly involved in interacting binaries, but we've had a very weak grip on binary red supergiants themselves. Before my other PhD student, Catherine Nugent, started her project, we knew about maybe a dozen red supergiants that had been observed with companions. And they were mostly systems like this. So this is VV Cephei. It's this gorgeous eclipsing binary in the Milky Way where you have an M2 supergiant and a B star orbiting in the star's wind, essentially. So it's an interesting scenario because it is an interacting system from the perspective of the B star, but not from the perspective of the red supergiant. The red supergiant is losing mass, as it always has. It is not directly overflowing its Roche lobe and undergoing mass transfer. The B star is basically picking up mass that the red supergiant has already put down. It's been gorgeously observed by Hubble because since it's an eclipsing binary, you can actually study the blue supergiant as it emerges from behind the star and is sort of shining through the red supergiant's wind. There are a handful of systems like VV Cephei, some are eclipsing, some are not, but they're all these red supergiants with wide B star binaries in elliptical orbit, so it looks like we really haven't seen official mass transfer between the two yet. There's a counterpart system to this with K-type red supergiants, not M-type, and I like doing this just because it shows you the scale difference between K supergiants and M supergiants. So this is to scale how these two systems compare, but I'll blow up the K-star system. So this is Zeta Aurigae. It's another case of an eclipsing system where you have, in this case, a K supergiant and a elliptical orbiting B star coming through the wind. So we had about a dozen of these in total in the many, many red supergiants that we had studied. So the question had then become, we need to quantify what the binary population is for red supergiants, it's a first step toward figuring out how many are interacting, how many may have already merged, how many are truly single, and what it means for their evolution. And since we hadn't seen any, the question became, well, are we missing them? So how do we actually identify red supergiants and binaries? Their light curves are out, because these stars have big boiling surfaces that mess with what we see as their V or even K magnitudes. We also have these stars being pulsationally unstable. They're photometrically variable anyway. There are far too many things going on to figure out an observational signature for a binary companion just from visual variations. What you can do is look at the spectrum. So Catherine Nugent, for her thesis, is looking at red supergiants and binaries in all of their various forms. And one of her first projects was looking at potential binary signatures in a red supergiant spectrum. So this is a red supergiant that at a glance might look single. It just looks like a normal, kind of on the warmer side red supergiant with some titanium lines. But if you zoom in on the blue end, you see these strong, higher order Balmer lines. Those are the signature of a B star companion. She actually ran through evolutionary models, and mathematically, almost all red supergiants will have B stars for companions. A handful will have O stars, but they're much rarer. By the time the companion is an A star on the main sequence, the red supergiant has died. So the vast majority of red supergiants will have B star companions, maybe a few will have O stars, or the red supergiants will be secondaries with something like a Wolf-Rayet star as the hot companion. From this, you can actually figure out what different composite spectra of binary red supergiants would look like. This is a 3,500 Kelvin, so fairly cold red supergiant with a very hot B dwarf companion, a warmer red supergiant with the same B dwarf companion, and so on. And you can see what this does to the star's SED. They're very oddly shaped. It means that you should be able to identify them by colors. If we take these as 4 example SEDs and drop them onto a color plot, so this is U minus B versus R minus I, single model spectra for red supergiants land here. Single model spectra for B stars land here, and everything in the middle is a composite. I keep referring to this as the duck head diagram, but you can see this triangular region where the stars should land. If you then put real stars on here, you can see that we get a lot of actual red supergiant binaries. You get some contaminants like quasars will drift in, yellow stars will drift in, some B stars are weirdly red due to extinction or similar, but all of the red supergiant binaries are contained in here. So Catherine's first paper was looking at the photometric criteria for finding these, and she then went and did spectroscopic follow-up of them. You can do nice long exposures of very nearby, very bright Milky Way stars because you're looking in the U and B band where there's no light. From these, we were able to find a ton of signatures of B star companions. So this actually wound up quintupling the number of known red supergiant binaries. We went from 12-ish to 100, around the order of 100. She is just getting back from observing around in Chile, where she extended this to the Magellanic Clouds and was sending me spectra going, look, we found another B star. Look, we found a BE star, which is really weird. And identifying new hot companions. We still do find plenty of single stars. We can quantify, based on the different types of spectra that we're getting, whether there could be a B star there and we're just missing it, versus whether the B stars are well and truly not present. And we do still find single red supergiants, but the number with B star signatures has gone up. So the next questions are now everything else on this list. Finding a companion is one question. We want to know whether they are interacting. We want to know whether we see signatures of red supergiant variability, and for the ones that look single, it would be great to know if some of them truly are, or if some of them have already expanded and swallowed their companions. Yeah?
So massive stars like to form in groups. How do you know it's the companion and not just another B star from the same birth population?
Yes, so a lot of this gets down to right now doing this in very uncrowded populations where we're not picking up just like a neighboring B star. It's impossible to know if we aren't just getting a red B star that's straight in front of it or close enough behind it that it would be involved in the composite spectrum. For now, what we want to do is start moving to a shell spectroscopy with these so we can get more velocity information, so we can figure out if they seem to share common extinction, and then from there looking to see if there's any signs of interaction. At the very least, if we were getting some, then that means the binary fraction would be even lower than we think, which would be surprising. So, But yeah, that's the next trick, is going from we see a B star with it to is it interacting with the B star? Could it potentially have already swallowed a star? And really all the other questions that come up when you think about red supergiants in binaries. If we talk about swallowing companions, we get to go to the very fun extreme of red supergiant binaries, which are Thorne-Titkoff objects. So these are a theoretical class of star where what you have at the end of what we think is binary evolution, a neutron star core that's surrounded by a very large diffuse envelope that from the outside looks exactly like a red supergiant. The only distinction between a normal red supergiant and a Thorne-Titkoff object from the outside is composition differences in the outer layers that come from that big convective zone in the red supergiant interacting with the very hot region near a neutron star. So this is how we think these form right now. You'll start out with two massive stars happily evolving away in a binary, and the primary in this case will evolve first. It may be too massive to ever become a red supergiant. It'll become a Wolf-Rayet star, at some point undergo core collapse. You get this beautiful supernova explosion. The people who animated this had fun with the camera shake. And what you're left behind with is a neutron star. When the secondary companion that expands and becomes a red supergiant, it will swallow the neutron star. The neutron star will spiral into the core. It actually disrupts core fusion in the star. There's some funny chemical signatures that come from that process. And what you're left with is a Thorne-Titkoff object. So back in 2014, we found the best candidate that anybody's identified so far for proving that Thorne-Titkoff objects are real. It's a star in the SMC that perfectly resembles an SMC red supergiant, but has the exact chemical profile that you would expect for a TZO. And we're currently looking for more so that we can go from the one object oddity to, by astronomy standards, 2, so then we'll have a class, and then 3, so we'll have a population. But as we get more of them, we'll at least be able to probe a little more